You would not think it by looking at it, but down there, in that ordinary green space below, is the location where one of the most unique phenomena to have ever occurred on Earth transpired. That is Oklo, in the country of Gabon in Eastern Africa. And it is the site of what was once the world's only natural nuclear fission reactor. That's right, you heard me correctly. It was a naturally occurring nuclear fission reactor. Now, by modern standards, it wasn't very powerful. It only produced about 100 kilowatts when it was fully active. And that was only for about a 30-minute period. But the phenomenon was remarkably stable, repeating this kind of energy production every 3 hours for 300,000 years. The set of circumstances that enabled this to come to pass were unlikely and incredible. Quite literally, they could only have happened about 1.7 billion years ago or earlier than that. And that's based on the age of our solar system, so a natural reactor cannot actually occur on Earth or any other body in our solar system anymore. Such things may have happened on other moons or planets, and while the circumstances that could create them would be exceedingly rare, given the vastness of those moons and planets, I think it's likely, but it could not have happened beyond about 1.5 billion years ago for reasons we'll discuss as we go along. But any way that you look at it, the fact that nature actually managed to produce a natural fission reactor, it's really quite remarkable. It is doubtless fortunate that it cannot happen today, as the appearance of natural nuclear reactors, they could be truly extraordinarily hazardous. In 1956, a Japanese-American physicist by the name of Paul Kuroda predicted the possibility for natural fission reactors. This was 14 years after the first experimental nuclear fission reaction had been conducted by physicist Enrico Fermi, who built Chicago Pile 1, the world's first nuclear reactor. Less than a decade later in Arco, Illinois, the world's first experimental breeder reactor, EBR-1, was created. From this early work, the world developed the technology to use uranium for something other than the creation of fission atomic bombs. Physicists had learned to set up sustainable fission chain reactions to generate power, but the circumstances by which this could be set up and sustained were extremely complex, and it took the application of an immense amount of skill and technology to make these reactors even happen. So when Paul Kuroda suggested that a natural nuclear reactor was possible, his prediction was very likely taken with not only a grain of salt, but probably a tablespoon of salt. And no one, I imagine, would have remotely suspected that not even 2 decades in the future, Kuroda's unlikely predictions would prove to be correct. The discovery of Earth's one and only known natural nuclear fission reactor occurred in 1972, when French scientists were examining the quality of hexafluoride samples that were being brought to them out of Oklo, Gabon, the site of a productive uranium mine in Eastern Africa. They noticed there was a discrepancy between the ratio of the isotopes uranium-235 and uranium-238. The ratio between the two isotopes was incorrect. The ore should have contained uranium-235 at levels of 0.72%. However, the levels were down to around 0.60%, though some sources say the levels were 0.717%. In either case, there was a discrepancy. And with uranium-235, discrepancies had to be sorted out. This was, after all, the kind of uranium that could be used to run reactors, but it was also the kind of uranium that can be used to make weapons, atomic bombs. So the scientists who observed this discrepancy immediately began to research the error. They went to the mine in Gabon, however, and found that the hexafluoride samples from all over the mine were also producing levels of 0.60% uranium-235, meaning that the phenomenon being observed was natural. In the physics community, this created quite a stir. It was a mystery. This was because the ratio between uranium-235 and 238 should be predictable and consistent all around the planet. Uranium-235 breaks down faster, with a half-life of about 700 million years, and uranium-238, while also radioactive and somewhat unstable, has a half-life of 4.5 billion years. This is roughly equivalent to the estimated age of the Earth. Since all the uranium on our planet arrived at the same time, the ratio between uranium-235 and 238 should be consistent and predictable wherever it is found anywhere on the planet. And yet, here in Oklo, it simply was not the case. So why is it that all the uranium on Earth would have arrived on the planet at around the same time? The generally accepted theory regarding the formation of the Earth as well as our entire star system, is that it all condensed 4.5 billion years ago out of a disk of interstellar dust. Essentially, a nebula. The Sun, all the planets, moons, and other bodies within our star system fundamentally share the same origin, as they all condensed out of the materials to be found locally within that cloud. There were some derivations from one point to another, which we see today in the differing compositions of our star system's varying planets. But the origin of the heavy materials within that dust cloud would have happened hundreds of millions, perhaps billions of years before, meaning those materials themselves had the same start or origin date. And so all the uranium that condensed into the dust cloud that ultimately formed Earth was of roughly the same age. And this idea or concept has borne the weight of scrutiny, as uranium-238 and 235 have been found in consistent and predictable ratios wherever they are to be found around the planet. So when there was a substantial inconsistency in the uranium-235 to 238 ratios found in the ore out of Oklo, Gabon, Africa, and only that location, it raised many a scientist's eyebrows. An investigation into the ores to be found at Oklo soon confirmed that the missing uranium-235 was not, thank goodness, the result of being carted off to would-be makers of weapons of mass destruction. The discrepancy was natural, and continued research in the area soon found a natural fossil reactor, a place where a fission chain reaction had been created and sustained entirely by natural forces. Let's take a look at how it worked. For it to work at all, several circumstances had to come together just right. One of them is that Oklo had particularly rich seams of uranium ore, some more than half a meter thick. Now, uranium is radioactive because its atoms are inherently unstable, and over time, the atoms will break down naturally, releasing some of their protons and neutrons along with a substantial wave of energy each time an atom breaks down. A nuclear chain reaction happens when one of those neutrons impacts another uranium atom, causing it also to break, releasing more neutrons. Now, while it is true that atoms are very small, the things they are made of, electrons, protons, and neutrons, are much smaller still. In fact, the vast majority of an atom, even a big atom like uranium, is simply empty space. And the odds of one of those neutrons managing to hit the nucleus of another uranium atom are inherently extremely small. Thus, a seam of nuclear ore must be quite thick to increase opportunities for escaping neutrons to strike other nuclei, thus creating a chain reaction. But wait, there's more. It takes more than just a thick seam of uranium or any other fissile material. There needs to be a moderator. A moderator is a material that slows down the speed of the neutrons that escape from atoms that break down, like uranium-235, creating more opportunity for those neutrons to strike other nuclei. And it turns out there are many things on Earth that can serve as moderators, such as graphene and also water. And 1.7 billion years ago, when this natural fission reactor was created, the uranium ore seams were to be found underground in the form of a rich black material called uraninite. And the ground above was porous. It also was at the bottom of a depression or slope where water could flow in. So water was able to naturally seep down and collect over the deposits of uraninite ore. But even then, all by itself, that would not have been enough. For a reactor like this to occur in nature, the amount of uranium-235 present would have to be around 3%. We've already noted that uranium-235 has a half-life of 700 million years. And this means that today, in all the uranium ore found all around the planet, the ratio of the percentage of uranium-235 to 238 is roughly 0.72%. Not nearly enough for a natural chain reaction to occur. But 1.7 billion years ago was a long time back, and much of the uranium-235 had not yet decayed. In fact, the ratio at that time was closer to 3%, a little over 4 times what it is now. So, in Oklo, Gabon, and only in Oklo, Gabon, rich, thick seams of uranium ore were to be found underground beneath a porous surface that allowed water to seep through. This water collected over the uraninite, serving as a moderator, slowing down the neutrons that were released through the natural decay of the uranium, working somewhat as a catalyst to allow many more of those neutrons to impact other uranium atoms, causing them to break down as well. Heat built up very quickly, superheating the water, which boiled away in roughly 30 minutes, shedding the reactor's heat. Things cooled down, water was once again able to pool over the uraninite, and over the next 2.5 hours, water quantities accumulated until it was sufficient again to serve as an effective moderator. Thus, this natural nuclear reactor cycled every 3 hours. producing a self-sustaining nuclear fission reaction for 30 minutes, and then cooling down once it had evaporated its moderator away. And amazingly, this process maintained for 300,000 years. Now, as noted at the beginning of this video, the Oklo reactor only produced about 100 kilowatts. So just what can you do with that much power? That might be enough to run a dozen homes or so, or 100 washing machines, or maybe 1,000 desktop computers if they weren't being used for heavy work, like editing video, like these videos. Or maybe 1 million or so tiny LED bulbs. Overall, it's not a lot of power production. Though of course that power was not being used for anything. 1.7 billion years ago, there was no complex life on the planet. This was long before even the age of the dinosaurs. However, this is an incredible example of how, on its own, nature can accomplish almost anything. And while we don't know of any other natural nuclear fission reactors on Earth, we do know that nuclear reactions are a common natural phenomenon. Look up into the sky by day. The sun is a nuclear fusion reactor. Look into the sky by night. Every single star that you see is a natural nuclear fusion reactor. In fact, most of the matter that you can see with the naked eye all throughout the universe exists in the form of plasma surrounding those natural nuclear reactors. It's ironic, isn't it? It took humans with PhDs, the most brilliant minds with doctorates in physics and related fields, to create nuclear fission reactors. And it turned out that long before there were ever even humans walking the face of this planet, nature had managed it all on her own. Thank you for watching. The Naturalist program is committed to the reliable coverage of natural science and environmental issues. If you like our program, please take a moment to subscribe and like.